Okay, so we're going to continue on the notes. This is part 2 of chapter 5 notes, and what we're doing now is about several gas laws. The first one being something called Boyle's law. Boyle's law is the relationship between pressure, P, and volume of a gas, V. So pressure, P, volume of gas, V. Pressure, as in the last part of notes, pressure can be measured in a whole bunch of different units from atmospheres, as it is written here. It also could be in millimeters of mercury, also known as torrs, or it could be in kilopascals. Here, we're just going to be using atmospheres. Okay, oops, I went way too far. I don't know why this thing, okay, there we go. Okay, so we'll be using atmospheres for this thing. The relationship between pressure and volume, well, they are what's considered inversely proportional. What that means is as one goes up, the other goes down. And by the way, in Boyle's law, one thing we're assuming always constant temperature and constant amount of gas. That is the same temperature, that we're not heating up, we're not cooling it down, and that it's the same amount of gas. So imagine like a balloon. You had a balloon full of, obviously, with gas in it. Could be air, doesn't matter what kind of gas is in it. So you have a balloon and it's just at room temperature. What happens as you increase the pressure, or how could you increase the pressure? Squeeze the balloon. And as you increase the pressure, you probably would kind of imagine that as you increase pressure, the volume would decrease. Or you could say if you release some of the pressure, the volume will increase. So that's Boyle's law that is inversely proportional. As one goes up, it's kind of like a seesaw. As one side goes up, the other side goes down. If one side goes down, the other side must go up. So as the pressure goes up, the volume must go down. Or as the volume goes up, the pressure must go down. So that's the what it means by it's inversely proportional. Or you can say, hey, as 1 over the volume increases, the pressure goes up. Okay, the inverse of one of them. As the inverse of one of them goes up, then the other one goes up. That's what it means by inversely proportional. Sometimes it's written like this. P is proportional. This little, looks like a little fish-like symbol. Just means proportional to. Pressure is proportional to 1 over volume. Or another way it was written as pressure is equal to a constant times 1 over volume, or pressure times volume is constant. Okay, so lots of times these proportional means the same as pressure is equal to a constant times 1 over volume. Multiply both sides by V. P times V is constant. The pressure times volume of a gas at constant temperature and the same amount of gas doesn't change. So at this point here on the graph, 0.6 times 2, 1.2. At that point in the graph, 0.3 times 4 is equal to 1.2. At this point in the graph, whatever the pressure times volume is, it will equal to 1.2 for this specific gas. Okay, so the pressure times volume does not change. It's also written like this. P1 times V1 equals P2 times V2. The pressure of the gas times its volume equals a new pressure times its new volume. That's a time sign, not an X. P1 times V1 equals P2 times V2. So pressure times volume equals new pressure times new volume. Okay, again, we are assuming constant temperature, constant amount of gas in Boyle's law. So let's look at a sample question of this. Here it says you have a sample of chlorine gas, occupies a volume of 946 milliliters, a pressure of 726 millimeters of mercury. What is the pressure of the gas in millimeters of mercury if the volumes are reduced at constant temperature to 154 milliliters? Okay, well, let's just get some of the given down. I see the volume is 946, pressure is 726 millimeters of mercury. Oh, first that's the equation. So the P1, the pressure is 726. Do I know the original volume? Yeah, it says the volume of the gas occupies as 946. What else do I know? Do I know P2? What is the pressure of the gas? I have no idea. That's what I'm trying to solve. So P2, that's my unknown. Well, do I know V2, the final volume? It says, what is the pressure if the volume is reduced at constant temperature to 154? So I do know V2. So I know P1, I know V1, I know P2. Oh, sorry. I'm trying to find P2. And I know V2. If P1 times V1 equals P2 times V2, this is now just purely an algebra problem. You know, 3 of 4 variables. There are 4 variables in it, and I know 3 of 4. I'm solving for P2. Algebraically, I set it up this way. P2, if I'm solving for P2 there, divide both sides by V2, and I get this. Okay, P1 times V1 over V2. P1 times V1 over V2. Okay, plug it in. P1 is 726 millimeters mercury. V1 is 946 milliliters. V2 is 154 milliliters. Notice that milliliters and milliliters, the units cancel out. So my only units left are millimeters mercury. It'll be whatever 726 times 946 divided by 154. Actually, plug that in a calculator. What is 726 times 946 divided by 154? And yes, your answer should be, well, to 3 significant figures, 4460 millimeters mercury. And does that answer even make sense? Well, if you have a pressure 726 and volume 946, and you decrease the volume to 154, so it was, you know, almost a whole liter big, and you squeeze the gas down to 154 milliliters, well, that means the pressure inside must have increased. And yes, it did increase from 726 to 4460 millimeters of mercury. Okay, so this is all of at constant temperature. What happens if you have a gas that's not at constant temperature? So here's a gas in a tube, a very, very thin tube called a capillary tube. Doesn't really matter, but you got a tube with a mercury plug. Okay, the mercury is a liquid, it can go up and down. So if it expands, it'll go up, and if it contracts, it would go down. If you had the same gas at a low temperature, and you took that gas and heated it up to a higher temperature, right now it doesn't matter what the temperature is, but you had a low temperature gas and you had a high temperature gas. What do you notice about the volume of this gas? I think it's kind of obvious that as the temperature increases, the volume of gas increases. The relationship as one variable increases, the other one increases, that's also known as directly proportional. So the last one was indirectly proportional, that is, as one increases, the other decreases, like a seesaw. In directly proportional, if one goes up, the other goes up. If A goes up, B goes up. If A goes down, B goes down. So that's directly proportional. Here's the relationship between volume and temperature to gas. 4 different gases, they're just P1, P2, P3, P4, but 4 different gases here. And as you notice, as the temperature goes up for all 4 gases, as the temperature goes up, the volume increases for all of the gases. And it's a linear increase for all of these. Okay, so the only thing is for this, okay, we're going to do what's called Charles' law. We'll get to the second one called Gay-Lussac's law after. But for Charles' law, as the temperature goes up, the volume goes up. As the temperature goes down, the volume goes down. In other words, the volume is proportional, that symbol means proportional, to temperature. Also can be written as volume is equal to some sort of constant times temperature. Well, if V is equal to a constant times temperature, V divided by temperature must be constant. Or V divided by T never changes. Or V1 divided by, oops, I don't know how I'll get rid of that. Okay, V1 divided by T1 equals V2 divided by T2. The volume of a gas divided by its temperature equals the new volume divided by the new temperature. The only thing is the temperature units for this is not going to be Celsius, because if I said 0 degrees Celsius, you know you cannot divide by 0. But there is a unit in chemistry, a unit temperature in chemistry, that can never be 0. And that is the Kelvin temperature. Temperatures in this chapter, well, especially for the gas laws, will always be in the units of kelvins. So temperature must be in kelvins. You can never use Celsius nor Fahrenheit in the equation that has T in it. Pretty much for every equation in this chapter. So temperature must be in kelvins. As a reminder from chapter 1, Kelvin temperature is equal to Celsius temperature plus 273.15. 273 is good enough, but it's like pi. 3.14 is good enough, but 273.15 plus Celsius temperature is Kelvin temperature. So if it were 0 degrees Celsius, 0 plus 273 is 273. If it was 100 degrees Celsius, 100 plus 273 is 373. So if it was 25 degrees Celsius, 25 plus 273 is 298 kelvins. Now, where did this number 273 come from? It's not just something we made up, though you might think that. The 273, if for all these gases, doesn't matter gas 1, 2, 3, 4, as we decrease the temperature, the volume decreases. But they all, if we extrapolated the line for all of these gases, they would all have the same x-intercept. You probably learned that term, x-intercept, y-intercept, the same point where it crosses the x-axis. And at that point, the same x-intercept for all these gases are negative 273.15. Notice 273.15. So that number is just not just made up, but thin air. What that means is, and what is negative 273.15? If you theoretically had exactly that temperature. That temperature, also known as 0 kelvins or absolute zero, is when theoretically, ideally, well, not ideally, I shouldn't use that term, theoretically, where the volume is equal to 0. Your gas theoretically disappears. But that would make no sense. That's so it's more like asymptotes as it approaches that. Okay, you could never have actually 0 degrees Kelvin, because then therefore the volume would be equal to 0. There's actually an interesting thing that about 20 years ago, people tried to, some very obviously smart, famous scientists, tried to get to really, 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 really cold temperatures close to 0 degrees Kelvin. And from that, they actually discovered a fifth state of matter called a Bose-Einstein condensate. First hypothesized by famous scientists, Einstein and another one named Boyles. And that was finally discovered roughly about 20 years ago. From that, they were awarded the Nobel Prize in chemistry or physics. Okay, but either way, don't worry about that fifth state of matter, where it was only even discovered about 20 years ago. So don't worry about it. And you'll never really encounter it in any normal conditions ever. Okay, so, but there's no such thing as lower than that temperature, because that means, well, if you're at 0 degrees Kelvin, that means it doesn't exist, and obviously you're not going to have less than that, because that will be negative volume, which makes no sense. Okay, so let's look at a sample question with this. And the question reads, a sample carbon monoxide occupies 3.2 liters at 125 Celsius. At what temperature will the gas occupy a volume of 1.54 liters if the pressure remains constant? Okay, we're obviously going to use the equation V1 over T1 equals V2 over T2. Volume over temperature equals new volume over new temperature. Do I know the initial volume? Yeah, it was 3.2 liters. Do I know T1, the initial temperature, is 125? Whoa, I thought it was 125. I wrote 398.15. Why did I do that? Well, as you should remember, temperature in all the equations in this chapter have to be in the units kelvins. How do I get to kelvins? You're right. Take the Celsius temperature, 125, at 273.15, you get 398.15. So that's why T1 is 398.15. Okay, do I know V2, the final volume? Yeah, the volume is 1.54 liters. Do I know T2, the final temperature? No, that's the question. At what temperature will the gas occupy? So I'm trying to solve for T2. So V1 divided by T1 equals V2 over T2. From here, this is purely algebra. How you want to solve for an algebra problem, I actually don't care. Cross multiply, whatever, okay? Just plug it up to you. But algebraically, T2 is equal to V2 T1 over V1. Why? I actually cross multiply it first, then I solve for T2. Okay, but I did it in variable form first, then I plug it in. But up to you how you want to solve it. V2 is equal to 1.54 liters. T1 is equal to 398.15 kelvins. V1 is 3.2 liters. Notice liters and liters cancel out. So plug that in a calculator and see what you get. I got 192 kelvins. So the units, when you get this temperature, will be in kelvins. If you want Celsius back, okay, add 273 to get Kelvin temperature, subtract 273.15 if you want the Celsius temperature. So to get Kelvin temperature, add 273 to get kelvins, subtract 273 if you want this back in Celsius. It didn't specify what temperature, but if you want it back in Celsius, subtract 273.15. Okay, there's another one called Avogadro's law. That's volume is proportional to n, the number of moles. Or volume is equal to a constant times n. Oh, n stands for moles in this chapter. N for moles. N stands for moles. Okay, moles of obviously gas. This whole chapter is everything's a gas in this chapter. So volume is equal to constant times n, or V divided by n equals new volume divided by the new number of moles. Okay, this is actually to me like a stupid gas law. I shouldn't say stupid, but like common sense. As you increase the amount of gas, you increase the volume. Like if I had a balloon, if you added twice the amount of gas to it, it'll be twice as big. If you remove half the gas from a balloon, it'll be half as big. To me, it's like, duh. To me, it's a common sense. Avogadro's not famous for this law. He's famous for the other thing, Avogadro's number. But yes, Avogadro's law. The more gas you have, the bigger it takes. The less gas you have, the smaller it is. It's kind of almost like a common sense gas law. This is assuming constant pressure, constant temperature. Okay, and okay, I think we'll just stop there for now. And so that's it for today.